Good evening all. Let's get underway. Welcome to our webinar. My name is Graham Hunt. I'm co-convener of the Renew Sydney Central Branch, and on behalf of all the branch committee, it is good to see you all joining in. Welcome to you all, even if you are signing in locally from the Sydney region, elsewhere in Australia, or maybe even from overseas. It is exciting to be engaged with so many people. Firstly, I want to acknowledge the traditional owners of the land upon which the Sydney Central Branch operates, and from where I am at the moment, which is the land of the Gadigal clan of the Eora Nation. We acknowledge and pay our respects to the past, present, and future traditional custodians and elders of the whole nation. We also acknowledge their sustainable stewardship of First Nations people over the country for many millennia. Please feel free to let us know where you're joining us from in the chat box. Before we start the formal proceedings, I'd like to make a couple of announcements about future upcoming events the branch is going to hold. On the 14th of March, from 6:30 p.m. to 8 p.m, we are very excited to announce we'll be having a webinar, and hopefully, perhaps on the 12th of March, a site visit of a Mirvac apartment which demonstrate the use of green ceramics, developed by the New South Wales Australian of the Year, Professor Veena Sahajiwala, who will be joining us. Full details are still to be confirmed, so keep an eye on your email for that. In April, we'll be hosting a webinar with Michael Lee, Research and Analysis Manager from Climate Works. The topic will be proposed changes to the residential energy efficiency provisions of the National Construction Code, which are about to be updated with a significant increase in stringency proposed after a long delay. In May, we are still working on the details, but we're hoping to have a webinar in coalition with the Western Sydney branch of Renew, as well as the Coalition of Western Sydney Councils, on the topic of cooling the city. So again, look out for details of that. But tonight, though, we have the pleasure of welcoming Padraig Healy, Director of Sustainability at Credwell, Building Regulation and Sustainability Consultants based in Sydney. Padraig will talk to us on designing for mitigation of condensation in new homes. He has a Bachelor of Engineering and a Masters of Science of Sustainable Design, with over 10 years experience in the field of environmental sustainable design. We will go through the questions at the end of the presentation. Often we get more questions than we'll have time for, so please be patient. For the answering of the questions, I will be assisted by two of our committee members, Reshma Punjabi and Vasilius Giotis. So now I'd like to hand over to Patrick. Thank you.
Hello guys, thank you for that nice introduction, Graham. And thank you to the Renew team for getting in touch and providing me with this opportunity to talk about condensation. A very important topic right now, has been for the last couple of years. And it's great that we're starting to talk about it. So let me just bring up my slides and go through that with you guys. So yeah, basically my name's Padraig, Paddy for short, or just to be easier for everyone to understand and stops me from explaining it to everyone as well, numerous occasions, or Patrick even, the patron saint of Ireland. So I'm director of Credwell. We started up in 2000, I came here in 2012. We started Credwell ESD in 2018. I was working here in the same capacity from 2012 to 2018 and decided to join a former director who created Credwell. And we also work in the BCA access field which is basically certifying or helping certifiers make their houses, BCA and access reports for certifiers to make sure the houses are designed correctly. So going on from that, the agenda today is basically an overview of the condensation and risks associated within buildings. What that means in the construction code. The construction code is now geared towards that. Finally, in 2019, they brought in a section, F4.6, to deal with condensation. Before that, there was nothing. I will overview the hydrothermal software. I specifically use one called WUFI to analyze this risk in new buildings. And I'll go through a couple of examples of good design, basically, as well for you guys. So to start it off, what is condensation? I think everybody knows what that is. It's basically where moisture-laden air meets a cold surface, and it gets to a point where it hits its dew point, and then that vapor in the air turns into condensation or liquid. So essentially, that's easy to explain, and everybody knows examples of that. You see it on the windows, for example, there, condensation written on that window. And I remember in Ireland 25 years ago when I was in school, and it was very warm inside the school and very cold outside the school, we were having these issues, and we were drawn on the windows in our actual school because of the vapor condensating on the school windows, and they were single glazing at the time. So that's just a brief overview of what condensation is. There's two different types of condensation, I would say. Obvious condensation, so it's stuff that you can see physically in front of you, like what I described on a window pane. Maybe on a wall, after a while, you'll see it build up behind it. You might see, physical manifestation of condensation. The other ones are not so obvious, is when it gets into the wall and it hides in the wall. So water vapor gets through that wall and then it condensates within the wall. So that's called interstitial condensation. So that's the one that we're worried about as well in buildings specifically. And it's not the one that you go into a building and would see it, but a lot of these buildings that have been built may have interstitial condensation and we wouldn't know. We're not sticking our head in walls every day. Going forward, the risks associated, why is it an issue? Well, there's a lot of risks associated with condensation. Essentially, those nice looking fellows on the right are, I suppose, what you call dust mites, and they proliferate at about 50% humidity or more over a long period of time. Mold, obviously, mildew and fungi growth are also other issues to do with condensation. And it's not, if we can drain it properly and get rid of it properly and quickly, it's not an issue. But if it festers for a long time and it's damp for a long time and we can't mitigate those issues, that's when it starts to become a problem, like what you see here with these examples: mold, mildew, and fungi growth. So another issue with that as well, okay, so mold, what's the problem with mold? Mold and fungi, if they get into your airways, can cause problems. So, if you are susceptible to breathing problems, you may have issues with mold. So you're talking about harmful bacteria fungi getting into your airways and causing issues. So asthma would be an example of that. It can cause or develop issues like that, or it can make them a lot worse. So this is a graph here for you guys. I'm trying to put in a few graphs so you can see items, and it makes it more interactive. If you see on this graph, you can see temperature ranges of indoor surfaces, relative humidity levels, and basically, if you had your temperature between 21 and 24 degrees, which is what our comfortable range is for people to feel comfortable, is 21 and 24. So they're the ones we're kind of worried about, because we're trying to design our aircon to be between 21 and 24. You ideally want to keep it below 50% humidity, because above that you'll see dust mites proliferate. For an example, you need to be above 20 degrees or more to avoid mold growth. essentially. And you can see as it gets up to 70 and more, that's when we're starting to have problems. So a lot of our buildings actually have 60, 70, 80%, especially in Sydney, beside the sea in this climate, a lot of high relative humidity. You can see also that when it gets to below 21, that's where we have an issue. So in colder climates, Canberra, etc., the Alpine regions, down where the snow is, basically, you'll see that those buildings need to be kept warm. Otherwise, we have a lot of these issues coming across. Moving on. So I'd like to give an overview, as I said, kind of pictures are better. So these two examples are actually within the guide condensation within the BCA or the NCC. So these are actually in handbooks, which I give at a link at the end for anyone to look into. You can see here, so water vapor is driven by the differences in water vapor pressure. So obviously wind and it then moves from places of high to low pressures. So it's the same with water vapor. Water vapor wants to do the same, wants to get in or out depending on the pressure difference. So you can see down here on the left-hand side, a cold interior or a warm interior. When it's a warm interior inside, it basically wants to get out, and it's the opposite on the cooled interior. It wants to get from the outside to in. The problem recently is we've been sealing up our buildings more and more to become more energy efficient. So we're putting insulation within the walls in the roof, and then we're adding better sealing to our buildings. And that wasn't the typical design of Australian buildings in the past, where we did have quite a lot of leakage in the buildings, but that was kind of let go because it was some sort of uncontrolled infiltration, but it was helping towards passive cooling, basically. So now, to be more energy efficient and to meet the 2030 Paris Agreement, etc., we're striving towards more building sealing, more energy efficient buildings. And so that's why we're having condensation issues as a result as well. So what causes water vapor? So essentially in our house, dryers, washing machines, taps, us breathing and us sweating, transpiration, cooking and showers. So basically they give off a lot of water vapor, and water vapor is in our house, becomes humid. It wants to get out now. And if we don't give it a pathway to get out, it's gonna have problems. It's gonna get stuck in our walls. It's gonna condensate on our windows, and this is the issue now. So we can't tell people to stop, minimize their dryers. We could say get condensant and dryers. I can't say the word. I think you know what I mean. But you can't say to people to stop having showers, etc. So we need to mitigate these issues. So basically, the BCA in 2019 brought in Part F6 condensation management and Part 3.87. Now, the difference between those two is Part F6 is for Class 2, which is units, for example. Part 3.8.7 is condensation management within houses as well. So it just has, the BCA has, like everything else, is two codes, one for houses and one for units / bigger buildings, or Class 3 to 9 buildings, anything from offices to shops, etc. So it brought in this objective. The objective is reduction of risks associated with water vapor and condensation in buildings. So what they did was they brought in two major items. A pliable building membrane, if it's installed within a building, should be a vapor permeable membrane in climate zones 6, 7, and 8. Now, that basically means there's climate zones in New South Wales, in Australia in general. I think there's 8 or 9 in New South Wales alone. And we're basically, actually, no, I think that's too many. But 6, 7, and 8, 6, for example, is Western Sydney. 5 is the eastern suburbs. For example, when you get to Bankstown and go west, that's when we're talking about climate zone 6, 7, and 8. 6, 7, and 8 then are down in the colder regions. That vapor membrane needs to be a vapor permeable membrane. Now, I'll explain that just a little bit later on, what a vapor permeable membrane exactly is. And it also should be located on the exterior side of the primary insulation layer, so the exterior to the insulation. So your normal weather resistive barrier that we all have on our buildings, where you see it when a building's been built, you'll see the barrier around the building. That barrier now that is basically your pliable building membrane or your water resistive barrier, but it also needs to be vapor permeable now in these climate zones. So Bankstown West, but I would suggest not only in Bankstown West, it should be in anywhere in Sydney, vapor permeable membrane should be installed. The second thing, apart from the building membranes, is the flow and discharge of exhaust systems. So we're talking about making, in the BCA, there wasn't a reference to how much liters per second your kitchen had to exhaust to the outside or your bathroom had to exhaust to the outside. There was an Australian standard that talked about this, but it wasn't directly referenced in the BCA. So the BCA, as they say, the bouncing ball is you first comply with the BCA, and if the BCA says comply with an Australian standard, then you apply that Australian standard. So there was never a reference to the actual flow rate of kitchens, exhausts or laundries or bathroom exhaust before 2019. The next thing is about that is the exhaust from the kitchen or the laundries must be discharged directly to the outside. So no more recirculation kitchen fans. So every house, everybody would know of that fan that you put on in your kitchen about when you're cooking. It just recirculates it into the space or into the ceiling void, and that's it. So right now we need to exhaust that to the outside, get rid of that water vapor essentially. So what I was saying earlier about building membranes. So building membranes, it's like a good jacket. So like a North Face jacket, for example. I'm not trying to promote any types of jackets. I don't even have a North Face jacket. But basically a good jacket that, keeps the rain out. So the building keeps the rain out. But when you perspire, the jacket also lets your water vapor out as well. So it allows you to perspire, lets you sweat, so it's the same with a building. So a good building membrane, when all that vapor gets in the building due to all the water sources within the building, the pressure difference will be able to push that water vapor out through the building completely and doesn't get stuck by a vapor impermeable barrier where it just hits and stays within the building envelope or the exterior wall, within the exterior wall. So that's where we have the issues right now, where we have the condensation forming on the interior side of that vapor resistive barrier. So just like that diagram there, we want all that, the red dots, they want to get out. That's showing the water vapor getting out. The blue is showing the driving rain, stopping that from getting in. Moving on, then the second thing is the exhaust rates. So the exhaust rates, what I've just shown you here, that diagram in the bottom right, that shows what mechanical engineers will need to design for now. So mechanical engineers will need to think about, okay, we're exhausting air at a certain liter per second. That will depressurize a zone, which basically means they need to provide makeup air into that space so that it actually gets that 40 liters per second out through the kitchen exhaust. So to get it out, you need to put it in. So we need to provide or supply air into the space so that it can be exhausted. And when it's getting exhausted, then it can bring through that moisture-laden air out through the building. So as I said, point number 3 there, possible introduction of more risers in buildings to provide for that makeup air. I have a couple of examples later on as well, where you could provide that makeup air passively as well. There'll be no more recirculating kitchen fans. So if any of you guys are building or buying houses and you see recirculating kitchen fans, it's not allowed right now. You should get rid of it. And no dumping of cooking vapor into ceiling spaces or exhausting of any showers into ceiling spaces. That's just terrible. this is a bit of a technical, I suppose if you're a building certifier or anyone along those lines, you want to find out what is a vapor permeable membrane. How do I figure out I'm using the right one? Well, on the left-hand side is the definition. A vapor permeable barrier, class 3 and 4, tells you what the vapor permanence needs to be, rating. And then on the right-hand side is a typical example of an actual product details, where it says what classification it meets and what vapor permeability the membrane meets as well. So I just wanted to show that to anyone who is actually practically building or looking at putting in vapor membranes. So then moving on to our software. So as I said, 2019, this came in. 2019, like everything else in the BCA, you can do what's called a deemed to satisfy approach, which is a clause by clause approach to complying with the building code. So if you do this is like a recipe for a cookbook. You do this, and this, then you comply. Or you can also comply by using performance solutions or software modeling. So it'd be like a JV3 report for section J. It can be like, for this, for example, it's called an FV6, a condensation management report. So it's basically allowing you to use different membranes. It's allowing you to put in different products in the wall to assess how well that wall or roof is against condensation and mitigation of mold growth, etc. within the wall. You can see here a list of all the items that they look for and your software that you use. Now, there's more than one software, but the softwares that we use need to meet all these criteria. This is an example of one of the softwares that we use. It's called WUFI Pro. And you can see on the left is just a typical screenshot of the project details. And I'm in one of the tabs there. Basically, I just wanted to kind of give you an overview of what that looks like. And then on the right-hand side, then it shows you kind of the water content of each individual layer within the wall makeup. So for example, we have to follow an ASHRAE standard to make sure that we do these simulations correctly. And then that ASHRAE standard will tell us certain items that we need to comply with. So for example, when we start our modeling on this, we pick our wall, we put in all the different elements to the wall, and we tell it then, you know, we need to saturate those elements. So we saturate it, which means basically as if it was pouring rain on the building. And now this is worst case scenario. We have to design for future longevity of the wall, or see how that vapor and moisture gets out of those building materials. So we run this analysis for 10 years. So you hit the button, you run it, and you see, does that moisture get out of the wall, essentially. This is kind of an example of that here. You can see on the left, it shows up and down. I suppose it's like a heartbeat monitor. My wife gave birth recently, and I was watching the heartbeat of the baby. I was, you know, I couldn't stop looking at it. I was like, oh my God, hopefully that keeps going. But you can see it's a bit like that. You want that to go down as the years go on. You can see 2018, 2019, 2020, 2021. It's gradually reducing, which is showing good condensation management within the building after it's built over a period of time. It will dry out, basically. On the right is the outputs, the traffic signal outputs. Green is obviously good. Green is go. Amber is okay, it passes. It's below what's called a mold growth index of 3. So it still passes, it's up to 1.25 there. We're getting an amber light. It's not great, but it works. Maybe we do something to change that, make it better. And I have a video as well that I can show you guys just quickly on the outputs. So I'll run this quickly here. So this is the software. As I said, you click play essentially on it. So this guy, I think he talks for a little bit and it hits play. And you can see it moving from 2015. That's the clock. It goes, he's very slow actually, he's winding it up. March, April, May. You can see here the different relative humidity. You can see the solar radiation in red hitting the building. And then on the bottom there, the blue lines show the actual water content and where it's resting. So you can see, I don't want to get into too much detail, it's very technical, but the more of that blue on the bottom, on the right-hand side, shows towards the in, from left is outside, right is the inside of the building. The more moisture that we build up behind certain layers, the worse it is. So we try not to get moisture build up within these layers. Essentially, this is what we're doing. Moving on from that, I think maybe click outside. We get into the, I suppose, the interesting area. Examples of good design. So I suppose a lot of you have heard passive house. If you're interested in ESD and the growth of passive house, it's not growing as quickly as I wanted to grow in Australia. People argue that it's a great climate here already. Why do we need passive house? Does it work as well in New South Wales, better in Melbourne? That's a different argument for another day. Passive house is a great design. One of the elements of passive house is what's called is kind of a continuous ventilation. So what that is a heat recovery ventilator or an energy recovery ventilator. Essentially, it's controlling the amount of air change rate within the building, so you can actually control that. So you seal up our buildings perfectly, well, as best as we can. And there's a test for that. There's a pressure test, a blower door test, and that you get that test, and then you put in a heat recovery ventilator, and then it basically draws the air from the inside out and draws the outside air in, and it passes it through a heat exchanger. So that there on the left and the right is an example of that box. So the warm air that's coming out and the cold air that's coming in, the cold air that's coming in gets heated up to close to the temperature that you want. By doing that, it makes it more energy efficient. You can also get what the energy recovery ventilator has dehumidification on it as well. So that removes the humidity of the outside air as it's coming in as well. So it has that ability as well to do that. So we run this 24/7. And so that air is continuously being supplied into the building and taken out of the building at a constant rate. So it's more control of our environment. It's not passive. Sorry, it is. It's not passive as in windows opening and just I'll open a window now and I'll close it later. And I don't know how much humidity is coming through that window. I don't know how much outside air I'm actually getting through that. So it's more control of our environments. Like I said to people before, it's like designing for building on the moon or building on Mars. It's you take complete control of your environment with this sort of setup. So that's, you know, an example of good design, but this has to work in tandem with good sealing of buildings. You can't have a leaky building and use this as well. Moving on, you can see here, I give more practical examples of them installed, what they look like. I mean, there's different, so these are quite big units that are ducted. You can get ones that are spot just for a particular room, for example, in a wall. I was on the Bunnings website the other day and I was looking at, can you get one for just one particular room? And you can install just one for one particular room and just make that room super efficient if you want. But then, you know, this example, usually they're put into ceiling spaces or they're put somewhere out of people's sight because they're quite big. Another example of design, good design, would be trickle vents in windows. So we're talking about this makeup air and making sure that we have enough air getting into the building so that we can exhaust it. Trickle vents are great because trickle vents can be retrofitted as well. So for example, here, if you're looking at this diagram on the left-hand side, you can see a kind of a device above the window in the subframe there that you can flick open. So basically the middle picture shows it open there for you. And then the picture on the right shows that the air goes through that subframe. There's actually filters in this one. There's dampers for noise in this one. And it also then lets that air in. So the idea of this is that it's also a control. So if you're having a shower, for example, if you're in, you would put this in a room that has a shower or a window beside a shower. You flick it open. If you remember to do this, flick it open, have your shower, provide that makeup air for your exhaust. You may leave it open all the time if you want to, if you don't feel it's causing any, comfort problems. So yeah, it's this trickle vents. They're becoming more and more popular, and we're trying to convince people to actually put them into the design of their houses. So they consider trickle vents. Now, you don't have to put a trickle vent in every single window in your house, but for the main areas like the shower and stuff like that, was a lot of moisture buildup, you would kind of want control or more control of that. And then I suppose I've highlighted a few items here as well in terms of good design. We all know what a whirlybird is. So there's a picture of a whirlybird that gets rid of the heat in your roof space. It will also get rid of the moisture in your roof space. That's obviously a very old technique of doing that. There was, I think Graham might know from previous experience how Australian buildings, that was probably one of the first problems before even insulation was put in, was really hot attic spaces that we wanted to vent. We want to have double glazing windows. So we want to stop that contact between a really cold surface and a really moisture laden humid air and it condensating. So if you have two panes of glass, that will not happen. So we want double glazing. We want thermally broken frames. A thermally broken frame is like that picture that shows the glass in the frame there. So if you look at the frame, you can see kind of a honeycomb structure in that. So the more fine that is, the more efficient your U value, or the more efficient your frame is, essentially. So we want to have good thermally broken frames. We want materials with high moisture content storage. So what does that mean? It's part of the modeling process that we go through. We pick materials, let's say, for example, that have high moisture content. So for example, wood has a good moisture content storage. It's natural. Wood contains moisture, it holds it well, and then releases it well also. It's very natural. Rather than having a stud wall is metal. It does not hold moisture, does not get rid of it. Although the issue with wood is mold can grow on wood. So that's why we need to assess that it works also. Porous, breathable building membranes and construction materials. So not only the membranes that we use, but the insulation that we use. For example, glass wool insulation is breathable. Rock wool insulation is breathable. What that means is it lets the water vapor in and out. PIR board, polyurethane board, phenolic board, they're kind of derivatives of oil and gas. They're man-made materials. They're inert materials. They block vapor going through them. So that will stop, that will, basically act like a vapor barrier as well. So if you have a vapor barrier and you have rigid board insulation in your walls, it's stopping that moisture from getting out. So that's why we always suggest use, porous building materials along with porous building membranes. Don't use a breathable membrane, but then stick in, a non-breathable product like insulation product, for example. Saturation of the building, we need to start talking about, if we know it's going to rain, it's going to be a bad year for rain like it is this year, we want to cover up our buildings to stop moisture from getting into the buildings when it's been designed. So when we get big rainfalls, we try and mitigate the amount of rain that gets into the building, so we don't have to actually try and design as much to get rid of that, because that is an issue. Well ventilated cavities and roofs. So obviously that's a very obvious one. We need, the picture there shows you air in, air out. We need weep holes in the walls. We need to have an air change to get rid of that vapor that gets in to the wall. And we need, I have also at the very end there nominated, and this is the future as well of membranes. It's called a humidity variable airtight membrane. So these membranes are put on the inside of a building to seal the building up, and they can detect how humid the air is, and then the molecular structure within that membrane can change to allow the moisture or the water vapor to get out through the membrane as needed. So if it gets too high, it gets to 60% or whatever, it changes and allows that water vapor out. And it works in the opposite. If it wants to stop it from coming in, it will do that as well. So that's the kind of like intelligent membranes that we're starting to look at now and into the future. And then just to wrap it up, there is resources that everybody can look at. If you want to take a screenshot of that, for example, condensation in buildings, the Tasmanian condensation buildings. And to be fair, the Tasmanians have been on top of this for a long time, prior to any other state in Australia. And I think there's a university in Hobart or the other city that's there. They have quite a good team or lecturers that have looked into this specifically, because obviously in Tasmania there has been some issues because it's a colder climate. And then on the right hand side is the ASHRAE standard that we use to basically model for vapor in buildings and vapor management in buildings and condensation. So that's basically it. If anyone has any questions for me, I'd be happy to answer, or if Graham wants to jump in and
Yes, thanks, Padraig. That was very comprehensive and interesting. It's a challenging area, so it's good to get a good understanding of it. We have at the moment 10 questions, so we try and get through them. There's one from Simi, which has sort of come in several parts, so I'll combine them into one. Simi's asking, if you're making a dwelling out of shipping containers, what insulation is best, please? She says she has been recommended to use cell spray foam, closed cell spray foam, with a 15mm eco ply on top of that. Your thoughts, please?
Yes, I would actually. So when I mentioned earlier, you can design our buildings to be vapor permeable or vapor impermeable, but you pick one. So you want it to be, there's no other option with this metal. I think you need to have a vapor impermeable building, but then manage your moisture in other ways. Like I said, make up air get into that building and exhaust it. So the foam is actually really good, because the foam with the corrugated iron, obviously, as you know, comes in waves, and it'll be able to actually move into those cavities nicely for you. The only thing I would say with it sometimes is that it doesn't have as good an R value sometimes compared to some of the other products out there. So I would, it's still great. I mean, it's all insulation. It's the R value is what we're looking at. The R value is the resistive value to heat transfer. So the thicker that is, the better. So the thicker you want it, you make that spray foam, the thicker you make it, the better it will be. And you don't want those cavities, I'm guessing, because there's other issues there as well, with things getting in there, creepy crawlies might get into it. So if you're putting a rigid board insulation flush on a corrugated, you'll have those little gaps, and you don't want to have those gaps. So I would use in this scenario, expandable foam as well, for sure.
Okay, you wouldn't be concerned. My concern with some of those insulations is that they can off gas over time. They break down. Yes,
and it is an issue how sustainable they are, I suppose. And then also you need to look at a couple of properties. You want to look at your product details. You need to look at a couple of things like your flammability index, your spread of flame index. That will come in the brochure. You should look at that. You want basically 0 or 1 on that. So you kind of want ones that are also not combustible if possible. Make insulation not combustible is a hard thing, but there is products out there that are not combustible. And there is expandable foam out there that's not combustible. And I know of one product, I think it's TBA Fireflies foam, that is non-combustible. And, you know, that's the sort of product you'd probably want to use in this scenario.
Okay, good. Move on to the next question, which is from James. He's asking, would you recommend Vapour Permeable membranes in the Upper Blue Mountains, Wentworth Falls? I mean, you did say throughout the Sydney area is your recommendation, but I would suspect it's even more so in the Blue Mountains.
Yes, I would recommend it everywhere. So what I didn't explain about the climate zones is it's basically a climate zone 5 in Sydney is like, it doesn't have a big difference between indoor and outdoor temperatures to the rate, like the seasons aren't that different. For example, when you go to the Blue Mountains, you go to climate zone 6 and more, you have what it's called is a diurnal effect, temperature difference. So it's like a high difference between day and night. And with that then draws a lot of these pressure differences. It draws a lot of heat transfer, draws a lot of vapor pressure. It draws a lot of, you know, a lot of that. So that's kind of the reasons why they've kind of said, oh, you know, eastern suburbs is fine, although it's massively humid. But out in the west, you know, why specifically there is because of these big pressure differences and draws. So yes, 100% up your way it's needed. And yeah, vapor permeable barriers everywhere, 100%. You need to install them now. You don't want this interstitial condensation happening, be it in your roof or in your walls. And I had an earlier picture earlier on, very one of the pictures that showed a roof that was just covered in mold, all the rafters, because it wasn't ventilated correctly and the moisture wasn't getting out.
Okay, the next question is from Robert. He's considering adding blow-in insulation to retrofit a 1960s brick veneer house in southwestern Sydney. So the brick skin has vents for airflow, but he's concerned that may stop if he uses the blow-in insulation.
Oh no, that's been a proven method that works. So the issue, people think it's not an issue. So so if you're using rock wool beads and you're pouring it into the cavity, it's been tested in Ireland for years. I mean, my parents did it at home in my house. So you blow it into the cavity, and the cavity was always there to get rid of the kind of moisture within the cavity when it got in. So it got past the first brick, and then the air movement would get rid of the moisture. So these beads, they're what's called is water-phobic or hydrophobic beads, and it basically stops the capillary action from the outside to the inside. So it'll reject that moisture transfer. So people kind of forget that they're actually designed to stop moisture going through these beads. So it will actually stop. So if you cap it off correctly and cap it at the bottom and the top, it becomes its own sealed environment. Water will not get into it because of these beads. So it works. All you need to do is just do a bit more research, look into it. I can guarantee you it works, and it'll give your house a great R value, and it's going to be the future. After putting insulation and ceilings, we're talking about replacing windows with double glazing, and then also putting beads and into the walls, into double brick walls.
So the next question is from Marcus. He said, there's a comment on your side about membranes, but they can only be installed during construction. How do you resolve issues in units or balancing, improving the ceiling of the building without creating a vapor trap? So I guess he's talking about existing buildings.
Yeah, so usually actually in the new BCA, there is a get out of jail free clause for concrete built buildings, if it's most high-res buildings are made out of concrete. And I suppose it's there because they say that, you know, concrete is very good resistance to the passage of, or the well, they say a well-drained cavity behind a concrete wall works. Essentially, they allow it, and you don't have to do any modeling to show that it passes. So apparently, it's okay. So how do we you know, drill into a wall? How do we, like, I mean, it's very hard to replace a membrane within an existing wall. Unfortunately, it's like one of those things. I think unless you fill the cavity again, I don't think, if it's not there, it's very hard to put it in, and this is the problem.
I imagine ventilation is probably what you would need to do to improve
well,
the
yes,
situation.
there should be, you know, weep holes as we go up the facade of the building, and they should be at the standard distances, and it should, as you go up a building, the pressure difference also increases on the windows, so the wind pressure increases. So technically, the higher you go up, the more wind pressure there is, and the more your cavities should ventilate. So again, all this is kind of considered, but if you're having issues, and the class 2 thing here in Australia, or sorry, New South Wales, has been an issue, and they've tried to mitigate it recently with bad builders, basically, and a lot of south-facing units getting these issues, having mold and condensation issues happening. You know, they even have said that the concrete on these buildings is actually making them so airtight, in fact, that the makeup air and the exhaust air that we were talking about earlier is the main issue with this. So your normal construction, timber construction on a normal house and stuff, we're still not doing pressure tests in our houses and our dwellings. Therefore, there is a lot of leakage still, a lot of leakage. But these concrete form buildings that are being built, class 2 units, they're actually quite airtight, but there's no makeup air into these spaces. And that's probably the big issue. It's probably not the membrane as such, because if it's well drained and has the cavity there, it should be okay. It's more to do with the exhausting of moisture.
Yeah, right. A question from Romy is, what do you do if you have a single skin masonry wall such as Hebel to achieve permeability?
To be honest, you shouldn't be building single skin. There should be stud behind that. And I think Hebel would say that as well. They have, every of their systems has the stud and the Hebel attached to the outside. I'm sure there is ways of doing that, but you would still need insulation. If you're talking about putting external insulation, or if you're putting insulation at all, put it externally, not internally. So then you use some thermal mass. Hebel is a great product. Hebel has acoustic, it's good acoustically, it's good thermally, it's good for sound. It has these little bubbles within the product that does that for it inherently. And it's a great product. But just note that I would just follow the manufacturer's recommendations. And usually they talk about having a stud wall internally on Hebel power panel or etc.
We have been using it a bit in our projects recently in a reverse situation where you, like you said, with the Hebel on the inside and then insulation and the other cladding on the outside. And we can then use the breathable membranes in that location. Peter Kennedy has a question. Is it realistic to keep relative humidity below 50% in Sydney because of the external high relative humidity levels? I guess the question is, how do you achieve that? You mentioned the heat recovery ventilation system. Are there other simpler approaches?
Well, I would suggest buying solar panels and then running all your appliances, for example, your aircon, off that. And that aircon, you have to remember, has dehumidification abilities as well. So when we're cooling in our environment, the aircon not only reduces, it's called a sensible cooling, which is reducing the air temperature from 26 degrees to 22 degrees. It also takes the moisture out of the air. So dehumidification, a good air conditioning, pretty much all air conditioners now have dehumidification as well. So obviously, you know, that's my best advice. If I was building a new house right now, I'd put on the biggest solar panel system I could find, and then I'd run all electrical appliances off that. Then, you know, I suppose, you know, like just put the air conditioning in as many rooms as possible, duct it in pretty much all the rooms. You know, can we passively stop humidity? Not really. I mean, it's going to get into our building. It's very hard to stop. It's like outside now. It's in Sydney. It's 85 or 80. Like, I mean, it's crazy in Sydney. There's no way of stopping the humidity from getting in. So the best thing is we can mitigate this and stop it from getting in through these kind of techniques. But it's going to get in, and the best thing we can do is use dehumidifiers, air conditioning, and you know, just trying to make ourselves comfortable. Like, I mean, and make it efficient. So always think about where the electricity comes from. If it comes from the grid, you know, make sure it comes from non-fossil fuel sources and stuff like that. And that's my best.
We have a question from Natalie is, how do buildings with indoor vertical garden walls manage condensation issues?
Oh, that's a good question.
It's ventilation again.
Yeah, again, yeah, it'd be ventilation. I mean, plants by themselves provide cooling if they're used in the correct way. If you're an architect, you're always told that if you have plants and you put them on a certain side of a building and the air is being blown, you know, just the normal pressure of the air, let's say southwesterly, what's that called? The air always blows predominantly from the northwest or the southwest. You put the plants on that side of the building, and then as the air goes over the plants, it cools it. So the plants have cooling effects. So that should work indoor as well. We're always promoting for IEQ, indoor environmental quality, to have plants because they detoxify the air. They provide this cooling. They actually take humidity out of the air. So, like, I mean, plants are great. You know, I would just make sure that you have enough air movement over the plants. So installing ceiling fans, for example, to recirculate that air. As long as the air has been blown over them, then they should work correctly, and you shouldn't have too many issues, in my opinion. I think that's the solution to that. Provide plenty of air movement.
We'll do a couple more quickly. A question from John, thanking you for the presentation. They're building and doing using ProClimate, which is a breathable membrane, external and internal wraps with double glazing. He's asking, should they also consider some sort of ventilation extraction in the roof space area above ceiling insulation?
Yeah, 100%. Please do what Jesse Clark tells you to do at ProClimate. He is one of the foremost people in this area. So straight away, you're onto a winner with using their products. Very variable, a very nice guy. So he's well, I mean, if you ring him up and ask him, there is different, you would have to ventilate your roof space for sure, 100%, and provide in your soffit boards ventilation through there and mesh, and then a whirlybird to exhaust that. But then, you know, again, Jesse's the best man to talk to regards that, because he knows his products inside out. So he will give you a couple of examples. But yes, and he can even run these models that I'm talking about in terms of showing that it actually works for your typical building.
I would support contacting Jesse. Our next question is from someone we know quite well, Sean Maxwell, who used to be with ProClimate and has given a presentation for us in the past. So he's asking a challenging question. Have you seen AIRAH DA07 which is basically the ASHRAE 160 standard for and adopted for use in Australia. And I know Jesse Clark's been promoting this as a new manual to use.
Yeah, I've heard of it, and I think we've actually have it in the office. I still refer back to the ASHRAE standard here, Sean. I should actually do a bit more research into it. I'm sure you're going to say I'm missing something here. But yeah, again, there you go. Sean Maxwell is pro climate and one of the forefront people in the industry in terms of building materials. So yeah, no, we have it in our office, and I remember ordering it and looking at it briefly, and then I'll have to dive into it again, because now I know there's something missing. There's something in there now that I need to figure out, I'm sure.
Okay, I think we can take one more question because we have gone a fair bit over time. The next question is from Adam. What are your comments on under metal roof sheeting insulation blanket for a sealed roof void versus a ventilated roof void and lesser insulation?
Can you say that again? Sorry.
I think he's looking for a comparison between having a anti-con blanket under your metal roof sheeting with a sealed roof void, as opposed to a ventilated roof void and lesser insulation. I would recommend you would have the breathable membrane under your roof sheeting rather with a cavity, rather than an anti-con blanket, which has the insulation against the roof sheeting, and ventilate the roof void. I'm not sure. What do you think?
I would agree with that assessment. I know there's been a lot of research done into above roof sheeting ventilation, and especially with issues with heat island effect and aluminium just getting to crazy temperatures. And, you know, I think that's been an issue, and, you know, trying to reduce it by light colors from the BCA and stuff like that. So, you know, trying to bounce the heat off the roof before it gets in, stop it from coming in, is the big issue with roofs, because it's getting hit most of the time of the day with the solar radiation. So we kind of want to stop that as much as possible by putting in light colors, high SRIs, low solar absorption materials, building products. Ventilate as much as we can. As I said, that above roof sheeting ventilation, it works. I've seen some things on that. So and then ventilating within the cavity as well. So yeah, exhaust as much as you can of that air as possible. Try and keep your temperatures down. Is my suggestion. So yeah, I'd agree with you, Graham.
Okay. I hate to say it, we have probably another 18 questions, and they're all very good. So I want to thank everyone for putting your questions in. We will try and compile them and respond to them, and perhaps email out a response for everyone to see. So I'd like to take this opportunity to thank Padraig for a great presentation and for answering the questions so well. Maybe it's a topic we have to address again, because obviously there's a lot of questions out there. But anyway, thanks again, Padraig.
Thank you very much. And I hope I wasn't too technical, and probably not technical enough for Sean Maxwell. But the idea of all this is just to get people an introduction into this area and trying to promote this area in general, because there's not enough promotion being done on this. And if I can get some of my information, the information that I know, to people to make more informed decisions and contact the right people and stuff like that, then it's only better. But as I said, everybody should do their own research, look into it as much as they can, you know, contact the right people, and get informed decisions, and then you can't go wrong. And I want to thank Renew for inviting me. I want to thank your yourself, Graham, Mia, and Marissa as well, the tech support, and Vasilius, and also Reshma, who's also part of my own team at Credwell, for initially contacting me and mentioning this to me. So thank you so much. And if anyone has any questions, just shoot me an email or get in touch with Renew, and I'm sure they'll give me your contact.
Right, thanks again, Padraig. And now I'd just like to remind people online who are not members of Renew to consider inviting you to join the member community at Renew, and you can do that by visiting the Renew website.